Assalamualaikum and good day everyone. I'm Madam Nur Hidayah binti Ahmad from Physics Unit KMPk. Today we will learn Chapter 5. The topic is Electromagnetic Induction. Okay, first let's look at the overview of the electromagnetic induction. First we have magnetic flux. The symbol is phi. We also have induced Emf. It is divided into two, which is Faraday's law and Lenz's law. I will explain these two important laws after this. Okay, so this is also the overview of the electromagnetic induction. Faraday's law summarizes the ways EMF can be induced. It can be in four ways. It is in a coil, in a moving conductor, for variation of angle, and for variation of current. The variation of current itself can be divided into two, which is self-induction and mutual induction. For self-induction is for own circuit, and for the mutual induction for nearby circuit. We also have energy stored. Let's look the learning outcome for 5.1, which is magnetic flux, and the symbol is phi. So here you have to define magnetic flux and use magnetic flux linkage. Alright, so 5.1 we have magnetic flux. The symbol is phi. What is magnetic flux? Okay, so magnetic flux is the number of magnetic field lines, okay, that passes through an area. This is the lines. This is the magnetic field lines. Magnetic field lines with arrow. Okay, magnetic field lines with an arrow. Okay, it is the scalar product of the magnetic field, magnetic flux density P and A, and this is the formula. Flux is equal to B dot A, or we can say BA cos theta, where theta is the angle between normal of A and B. Okay, kita tengok. Alright, so this is the pages, this is the normal of area, and this is B. Alright, so this is B. So this is the angle between B and A. Alright, angle between B and A. And the unit is Tesla meter square or Weber. Instead of magnetic flux, we have magnetic flux linkage. It is also known as total flux. Okay, total flux, where the relationship between the magnetic flux linkage and the magnetic flux is flux. The total flux is equal to N phi. The important things that you have to know is N. This N is the magnetic flux through each turn. This is the learning outcome for topic 5.2. In this subtopic, we will learn about Faraday's law and Lenz's law. You also have to derive and use induced Emf in a straight conductor, a coil, and a rotating coil. Alright, let's enjoy. This is two important laws in this topic. We have Faraday's law and Lenz's law. Faraday's law states that the magnitude of the induced Emf is proportional to the rate change of magnetic flux. Okay, EMF is directly proportional to the rate change of magnetic flux. Okay, we go to Lenz's law. Lenz's law states that the direction of induced Emf or induced current always oppose the change in the magnetic flux that producing it. Okay, when these two laws are summed up in the relationship, we have EMF is equal to negative d flux over dt. This negative means that the direction of induced EMF is always opposed the change of magnetic flux producing it. And then For a coil of n turns, we have EMF is equal to negative n d flux over dt, where this flux is flux final minus flux initial over t. The picture shows the simulation of Faraday's law, which the induced EMF is directly proportional to the rate change of magnetic flux. When there are relative motion between the permanent magnet bar, this is the permanent magnet bar, and the coil or solenoid here, so the induced EMF will be produced. That's why this voltmeters shows the deflection. Okay, when there are increasing or decreasing of magnetic flux, there will be induced EMF and induced current in the coil. Let's look at this experiment. When there is any relative motion between the coil and the bar magnet here, there is deflection of galvanometer. The deflection of galvanometer shows the existence of current. The current known as induced current. When the magnetic field lines through the coil changes, thus the induced EMF exists across the coil. Alright, so first we look at this picture. The bar magnet move towards loop. When the bar magnet is moved towards loops, so there are increasing of magnetic flux. Okay, the number of magnetic field lines that passes through an area is increased. Okay, that's why the galvanometer shows deflection. For this one, there are no relative motion between the bar magnet and loop, so the V is stationary. So when there are no relative motion between the magnet bar and the loop, so the galvanometer shows no deflection. For this one, the bar magnet is moved away from the loop. When moved away from the loop, the magnetic field lines across the area or the magnetic flux will be decreasing. So the galvanometer shows deflection. Okay, remember, when there are relative motion between the permanent magnet bar and the loop or the coil or the solenoid, so then the magnetic flux will be changing, either it is increasing or decreasing, and then the galvanometer shows deflection, indicating that current or EMF is set up in the circuit. Okay, then let's move to Lenz's law. Lenz's law states that the direction of induced EMF or induced current is always opposite the change in the magnetic flux that produces it. That's why in our calculation we have EMF induced is directly proportional to negative d flux over dt. This negative refers to Lenz's law, to oppose the change in the magnetic flux that produces it. Look at the permanent magnet bar. As the permanent magnet bar is moving towards the coil, it will be increasing the magnetic flux. Okay, as we learned before, magnetic flux is the number of magnetic field lines that passes through an area. So, number of magnetic flux will be increased. To oppose the change of magnetic flux, the coil near the permanent magnet bar must behave like north pole to decrease the magnetic flux. Okay, and then when the magnet bar is moving away from the coil, it will decreasing the magnetic flux. Okay, sikit saja magnetic flux yang masuk ke sini. Okay, ingat balik, magnetic flux is the number of magnetic field lines that passes through an area. To oppose the change of magnetic flux, the coil near the permanent magnetic bar must behave like south pole to increase the magnetic flux. Okay? The direction of induced current can be determined by using right-hand grid rule. Okay, look at the picture. The thumbs shows the north pole and the field, and your forefingers shows the current. You can hold the permanent magnet bar as shown in figure above. When the north pole of magnet bar is moved towards the coil, the number of magnetic flux will be increasing. So, to oppose the changes, the end of the coil will behave like north pole. Sebab north dengan north ni dia tak suka, dia akan repel. So, dia akan decreasing the magnetic flux. So, by using the right hand grid rules, kita hold the permanent magnet bar and our thumbs show the direction of north pole. So, our thumbs shows the direction of north pole. So, direction of current will be like this. So, this is the current flow where the galvanometer will be deflected to the right. Okay? Hold your permanent magnet bar by using your right hand like this. Alright, so when there is no relative motion between the bar magnet and the coil, there is no current flows. So, this one, V is equal to 0. There are no relative motion, no movement between the permanent magnet bar and the coil. And then, when we moving out the permanent magnet bar, the number of magnetic flux will be decreasing. So, to increase the magnetic flux macam mana? So, kita punya solenoid near the permanent magnet bar will behave like south pole. Alright, so ini akan jadi north pole. So, macam mana kita nak determine the direction? We use the right hand grid rules. So, direction of current will be like this. So, kasih sini. Alright. Okay, so macam ni lah. Okay, so the direction of current, the direction of the galvanometer will be to the left. Okay, now let's look at the picture. When the magnet bar is moved towards when the magnet bar is moved to the left or towards the coil, there will be an increasing in magnetic flux. Okay, there will be increasing in magnetic flux to the left. Alright, so there's the induced current produce magnetic flux to the right to oppose the changes. That's why this pole near the permanent magnet bar will also behave like north pole to decrease the increasing of the magnetic flux. Alright, so when we're using our right hand rule, okay, our thumb shows the north and then our forefingers shows the current, so that our induced current will be in clockwise direction. Okay, clockwise direction. Alright, so look at this picture. When the permagnet is moved to the right, there will be decreasing in magnetic flux. Okay, there will be decreasing in magnetic flux. So then the coil near the permanent magnet bar will behave like south pole to increase the decreasing. So then, using our right hand grip rule, so our north pole is our thumb and our forefingers shows the current, so the current will be in anti-clockwise direction. Anti-clockwise direction. Okay, look at this picture. Okay, sama saja sebenarnya. Alright, picture A. When the bar magnet is moved towards the coil, okay, move towards the coil, so then there will be an increasing of magnetic flux. So the pole So the pole near the permanent magnet bar will behave like north pole, okay, to decreasing the magnetic flux. Okay, so this one will be south pole. So using our right hand grip rule, so 4 fingers shows the direction of current. So direction of current is like this. This is the direction of current. So the galvanometer shows to the right. For picture B, it is stationary. While stationary, there are no current induced. Alright, for this one, the B is the permanent magnet bar is moving away from the coil, so then the magnetic flux will be decreasing. Magnetic flux decreasing. So to increase the magnetic flux, the coil near the permanent magnet bar will behave like south pole. This one is north pole. So again, using our right hand grip rule, so our galvanometer turn to the left. Alright, this one also stationary. There are no induced current. Okay, let's learn the induced EMF in a coil. We have two cases. The first one is the variation of magnetic field strength. When there are relative motion between the coil and the permanent magnet bar, the magnetic flux will be changing. Okay, the magnetic flux will be increasing or decreasing with time. So when the B is changing, so the magnetic flux through the area also changing. Based on the formula, EMF induced is equal to negative d flux over dt, which flux is B A over dt. So here, when B is changing, so the magnetic flux is changing, and the induced EMF and the current are generated. So by applying the Faraday's law, okay, we have EMF is equal to negative d flux over dt, and flux is equal to BA cos theta, where theta is the angle between normal of A and B. Alright, so we have B is changing. So B is changing, we have EMF is equal to negative A dB over dt. So EMF equal to negative A is for area, so we have B final minus B initial over time. Okay, so this is the calculation. For the n terms, the induced EMF will be EMF is equal to negative NA dB over dt, where N and A is constant. Okay, dB over dt is changing. Okay, it's changing. Let's consider the experiment above. When the bar magnet is moving to the loop, the number of magnetic field lines that passes through an area will be increasing. Alright, so the galvanometer will be deflected. As we know, when the bar magnet is moved to the coil, so then our magnetic field lines will be increasing. So Lenz law said to decrease the increasing mag, so our pole near the permanent magnet bar of the coil will behave like north pole, to decreasing the increasing of the magnetic flux. So this one will be acting as south pole. So using our right hand grip rule, so our induced current will be in clockwise direction. When in clockwise direction, our galvanometer will be deflected to the right, indicating that the current is produced in the circuit. This is an extra note for you. Moving a magnet near a coil will induce a current. According to Faraday's law, the induced current will produce induced magnetic field in the coil. The induced magnetic field always tries to keep the flux in the constant loop. Look at this picture. Okay, when the magnet bar is 30 here, so then the number of magnetic field lines cutting the coil is only 1. But when we move the permanent magnet bar into the coil, so then the number of magnetic field lines cutting the coil is 5. Okay, so tu menunjukkan adanya increasing in magnetic flux. Alright, so when bar magnet move towards solenoid, okay, first one, B induced will oppose to the B original to keep the flux in the loop constant. And then we can use our right hand rule to determine the direction of current. And then for this picture, the induced current is to the right. Okay, remember that your thumbs shows your north pole and your forefingers shows your induced current. Or you can explain like this by using Lenz's law. When magnet bar is inserted into the solenoid, the north pole will be induced on the right side of the coil to oppose the incoming north pole. And then by using right hand grip rule, the induced current will flow anti-clockwise direction so that the pointer deflects to the right. And then when the bar magnet is moved away from the solenoid, B induced will have the same direction as the B original to keep the flux in the loop constant. And then using right hand rule, we can determine the direction of the current, and the direction of induced current is to the left. Or you can explain like this. By Lenz's law, when the magnet is withdrawn or out ataupun away from the solenoid, the south pole will be induced in the right side of the coil to oppose the outgoing north pole. And then by using right hand grip rule, so the induced current will flow clockwise direction, so then the pointer deflects to the left. For this one, the magnet bar move towards the solenoid. Ini sama saja, just kita tukarkan saja dia punya direction permanent magnet bar. And this one, B induced will oppose to the B original to keep the flux in the loop or solenoid constant. And then using right hand rule again, we can determine the direction of the current, and the direction of current is to the left. For this one, when the bar magnet is away from the solenoid, B induced will same direction to B original to keep the flux in the loop or solenoid constant. Using right hand grip rule to determine the direction of current, the induced current will be to the right. Okay, you can see this picture to have clear information. Case number 2 is changing area in magnetic field. Okay, you can see this picture. When the coil is stretching, the area is reduced. We stretch the coil. Okay, the area is reduced. The magnetic flux through the coil will be changing. And then when the magnetic flux changing, the induced EMF and current are generated. Based on the formula, negative d flux over dt. The very formula. Okay, by applying Faraday's law, okay, once again we apply the Faraday's law. We have EMF is equal to flux over dt, where flux is equal to PA cos theta. So now P is constant. P is constant, and now the area is changing with time. So now for the formula, it's become EMF is equal to negative NB dA over dt, where this A is A final minus A initial over time. For this one, bar magnet and loop is stationary. So there are no relative motion between the permanent and the loop. So when there are no relative motion, there are no change in magnetic flux. When there are no change in magnetic flux, so there are no current induced. Okay, no induced current. So when there are no induced current, there are no EMF induced. So the galvanometer shows no deflection, meaning there are no induced current in the loop. So our galvanometer shows zero deflection. For this one, the permagnet is moved away from the loop. So there will be decreasing in number of magnetic field lines that passes through the loop. So Lancelot said, what? Lancelot said it will be increase. Okay, increase. So this pole near the permanent magnet bar will behave like south pole untuk tarik balik. Okay, tarik balik. So then this one will behave like north pole. And then our induced current will be produced. Okay, so using our right hand grip rule, so our induced current in the coil is in anti-clockwise direction. Okay, in anti-clockwise direction. So our galvanometer will be deflected to the left, indicating that there are induced current produced in the circuit. Okay, let's look at this simulation. So this simulation shows you that our thumbs shows the north of magnetic field and our forefingers shows the direction of induced current. Okay, this one is also like that. So this thumb shows the direction of north field and your forefingers shows the direction of induced current. Okay class, let's try this. As a permagnet passes through a coil, so this one, the permanent magnet bar is moving to the coil, so then the magnetic flux will be increasing. So let's say that if it opposes the changes, so then our pole near the permanent magnet bar will behave like north pole and this one will behave like south pole. So using our right hand grip rule, your thumbs shows your north and your fingers shows the current. So current will be up, downward. Okay, so the direction of galvanometer is to the right. For picture number 2, there are no relative motion between the permanent magnet bar and the loop. So our galvanometer shows no deflection, meaning there are no induced current in the circuit. For this one, the permanent magnet bar is moving away from the loop. Okay, so then it will be decreasing in magnetic flux. Tapi Lens cakap apa? Lens cakap dia nak oppose the changes. So the pole near the permanent magnet bar will behave like north pole. Okay, the other side will behave like south pole, and then using our right hand rule again. So your thumbs choose your north pole and your forefingers choose your current. So the current will be upward. Okay, current will be upward. So the galvanometer will be deflected to the left. For the induced EMF in a straight conductor, when the metal rod moves with constant speed, remember that the magnetic field B is constant. Remember, B constant. As the magnet is moved to the left, so the area of field lines being cutting is increased. Alright, so the area is increased. So this will be changing this flux, because flux is equal to BA. So here flux is changing because the area is changing. B still constant. Okay, BA. So according to Faraday's law, we have EMF directly proportional to negative d flux over dt. So because they are changing in magnetic flux, so the EMF will be induced. EMF will be induced, and then the current also will be induced. Alright, for the change of area of magnetic field lines, we have dA is equal to L dx. A is area, L is length, and X is the displacement. So for the derivation induced EMF on a straight conductor, by applying the Faraday's law, we have EMF is equal to negative d flux over dt. So then here, what is changing? Area is changing. So we have E equal to d flux over dt dBA over dt. So here B is constant, so we have dA over dt. So for dA over dt, sama juga dengan L dx over dt. So here the displacement is changing with time. So we have EMF is equal to B L, and dx over dt is our velocity. So here is the formula for EMF induced for the straight conductor, where B is magnetic field strength, L is length, V is velocity, and the theta is angle between B and V. So we can use EMF is equal to B LV sin theta. And then we can use the Fleming hand rule, where thumbs shows the motion, the fingers shows the magnetic field, and the third fingers shows the current. Okay. Induced EMF in a rotating coil. Alright, consider we have a coil of n turns. Each of area A is being rotated on the horizontal axis in its own plane at right angle perpendicular to the uniform magnetic field. And then, as the coil rotates with angular speed of omega, the orientation of the loop changes with time. The orientation here is the omega or theta t. Alright, so this is the derivation of induced EMF for the rotating coil by applying the equation of Faraday's law for n turns. Thus, the induced EMF is given by EMF is equal to negative n d flux over dt, where flux is equal to BA cos theta and theta is equal to omega t. But here, you have to remember that n, B, and A is constant. And the only changing is omega t, or the angle, the rotation angle. So after have the derivation, so we have the EMF induced for the rotating coil is E EMF is equal to NBA omega sin omega t.
We divide into 5 positions for one complete rotation. So the coil starts to rotate with its plane vertical. In this diagram, we can say that it starts from 0 degrees. So the rotation in this case is clockwise rotation. So 90 degrees, C 180 degrees, D 270 degrees, and the last complete rotation 360 degrees back to A position. And we also discuss how the EMF is induced in the coil at each position. Okay, first position A at 0 degrees. Direction of V is to the right, and the magnetic field north to south to the right also. So from the cross product L V cross B, we use Fleming's right hand rule. So direction of B is to the right. So the pointer of your hand shows to the right. And therefore the V is supposed to be upward. But in this case, the V is parallel to B. So that means no EMF is induced in the coil. So if we sketch a graph EMF against angles of rotation, so start from the origin 0 here. The second position 90 degrees. So now the coil is rotated to 90 degrees. Refer to the red mark here, line for the coil. So this time V direction is downward. B still the same to the right, and using Fleming's right hand rule, so the pointer of your finger shows to the right magnetic field B, and then the V is downward, and lastly the I is out of the screen, shown by the dot here. So refer to the coil here means direction is as drawn here. Okay, so therefore, at 90 degrees, the current is maximum. Okay, next, at position C, 180 degrees, so the coil continue to rotate until 180 degrees. So this time the V direction is to the left, and B magnetic field direction still the same, north to south. Using Fleming's right hand rule, so your pointer finger shows direction of B. The direction of V is supposed to be upward, but this time it's parallel. So V is parallel to B. So therefore, no EMF will be induced in the coil. So no current is induced at this position. So from the sketch, the graph sketch here, back to 0. Next, position D, 270 degrees. Magnetic field direction is to the right, but this time the V is upward. So using Fleming's right hand rule, B direction is to the right, the V position is upward, and lastly I is into the screen. So that's mean, as shown in the diagram here, position of the current is in the clockwise direction. So therefore, and this time for opposite direction, so therefore it is plotted down here. Next, back to position A. So for the one complete rotation, V direction is to the right, and B direction also to the right. Using Fleming's left hand rule, pointer of B magnetic field to the right, but the B, because it's parallel to the B, so that's mean no EMF is induced in the coil. So the graph now back to 0. So we get a sinusoidal graph using Fleming's left hand rule. So we get about this type of graph. It's a sinusoidal graph, EMF induced against rotational angle. Quantitatively, we are going to derive
the EMF is induced is alternating between positive and negative values. A graph of induced EMF against rotation angle is shown in figure. The maximum EMF is known as EP. The EMF is maximum when the plane of the coil is parallel to the field. And the EMF is 0 when the plane of the coil is perpendicular to the field. one way to generate EMF is to rotate a coil through the magnetic field. Remember, the B field is constant and the area of the loop is also constant. But the angle between the field and the loop is changing. So here you can see that this is the normal of coil plane and this is theta, where theta is the angle between normal of A and B. Atoms of coil with the same area will rotate in a uniform magnetic B field and with a constant angular velocity, but it changes in magnetic field with time, d flux over dt, but the changes is only the angle, not N, B and A, and then an induced EMF and current are generated. Learning outcome 5.3 Self-Inductance. At the end of the chapter, you should be able to define self-inductance and apply self-induction, where L is equal to negative flux over rate change of current for coil and solenoid, where L is equal to N flux over current, L coil is equal to mu naught N square A over 2R, L solenoid is equal to mu naught N square A over L. Definition of self-inductance. Self-induction is the production of EMF in a circuit due to the change of current in own circuit. When the current is changing, how the current is changing? By changing R. By changing this R, here shows that the resistor can be changing, creates a changing in magnetic field, and then will create an induced EMF to oppose the change according to Lenz's law. Initially, when the switch is closed, the current will produce in its own magnetic flux through the coil. The current will increase from 0 to maximum, and the magnetic flux due to the change of the current will increase with time. The increasing of the magnetic flux will create induced EMF, but in opposite direction. If the current decreases, the decreasing magnetic flux creates an induced EMF, but in same direction. Okay, next we go to self-inductance, which is L. What is self-inductance? It is the ratio of the self-induced EMF to the rate of change of current in the coil. Self-induced EMF to the rate change of current in the coil. Or when we analyze the formula, we have EMF is equal to negative L di over dt. From Faraday's law, we have EMF is equal to negative N d flux over dt. Okay, so then we rearrange the equation. We have negative N d flux over dt also equal to L di over dt. So we have L is equal to N flux over I for the formula for self-inductance. For self-inductance of a coil, we have L equal to N flux over I, where flux here is equal to BA. Actually, it is NBA, where N is the number of turns. It's the number of turns. Okay. So from chapter 4, we learned that B coil is equal to mu naught I over R. So we have L is equal to N flux over I. So we know that flux is equal to NBA over I. So L equal to N squared BA over I. So B is B coil, so N squared. B is mu naught I over 2R A over I. So we have L is equal to N squared mu naught A over 2R, because we can cancel off the I. So we have N squared mu naught A over 2R for self-inductance of a coil. For the self-inductance of the solenoid, we have L equal to N flux over I, but for B solenoid, we have mu naught N I over L. So then we rearrange the equation. So we have L solenoid is equal to mu naught N squared A over L. Next, for subtopic 5.4, we have energy stored in inductor. So here you have to derive and use the energy stored in an inductor, which is U is equal to half Li squared. U is energy, half L is self-inductance, and I is current. For the energy stored in inductor, what is inductor? An inductor is a circuit component, coil or solenoid, which produce self-induced Emf. What is the function of inductor? It is to control current and to store energy in form of magnetic field. And this is the formula for energy stored. This is the symbol for inductor. For the derivation for energy stored in inductor, we know that EMF is equal to L times the rate change of current. And we also know that the power received by the inductor at time t is P is equal to I EMF or IV. So P is equal to I EMF is L di over dt. Okay, where kita naikkan kat sini dt, so we have P dt. So here we know that power is the rate change of energy, or E over T. So we have P dt is also equal to du, the change of energy. So P dt is equal to IL di. So P dt is also equal to du, so du is equal to IL di. So we make an integration here. So du is IL di, so we integrate the equation, and then we have u is equal to half Li squared, where u represent energy stored, L represent self-inductance, and I represent electric current. This is the last subtopics for this chapter. We have mutual inductance. So first you have to define mutual inductance, and second you have to use mutual inductance, which M is equal to mu naught N1 N2 A over L between two coaxial solenoids. Before we go further for mutual inductance, we have to know what is mutual induction. Mutual induction is actually a process for EMF induced in a circuit by changing current in another nearby circuit. So look at this figure. Two coils placed side by side coaxially. Coil C1 is connected to a source of EMF. Coil 2 is connected to galvanometer. When current starts to flow in coil number 1, the flux will begin to build up inside the coil. The flux will also experienced by coil number 2. By Faraday's law, coil number 2 will experience an induced EMF. The production of induced EMF in a coil 2 caused by changing current in coil number 1 is known as mutual induction. Okay, look at this one. Increasing current in coil 1 produce the change of magnetic flux. This changes is experienced by loop 2 placed nearby. And then, according to Faraday's law, loop number 2 will experience an induced EMF. That's why this galvanometer will shows deflection. Right, if the current in coil 1 change at rate di/dt, the magnetic flux will change by d-flux over dt, and this will experience by coil number 2. The induced EMF in coil number 2 is EMF2 is directly proportional to the change of current in coil number 1. So we have EMF2 is equal to M d I1 over dt. So then, according to Faraday's law, we have EMF induced in coil 2 is equal to M2 d flux 2 over dt. So then we can combine these two equations. V2. So then we got M d I1 over dt is equal to M2 d flux 2 over dt. So then we have M is equal to N2 flux 2 over I1. So then, look your eyes and take a look at this figure. For this figure, the current in coil number 2 change at rate di over dt, the magnetic flux will change at d flux 2 over dt. This will experience by coil number 1. And then we have this one directly proportional to the rate change in coil number 2. The rate change of current in coil number 2. So we have MF1 is equal to MD I2 over dt. So then, according to Faraday's law, EMF induced in coil number 1 is E1 is equal to negative N1 d flux 1 over dt. So then we combine these two equations. So we got M d I2 over dt is equal to N1 d flux 1 over dt. So the resulting we have M equal to N1 flux 1 over I2. You can find that these two M is same. So we have M is equal to N1 plus 1 over I2 or equal to N2 flux 2 over I1. This is the mutual inductance. And the unit is Henry. Figure shows a long solenoid with cross-sectional area A and N1 turns, and it is surrounded by its center by a coil of N2 turns. I1 will start to flow in solenoid, and uniform magnetic field is generated at the center by the equation of B1 is equal to mu naught N1I over L. Actually, the equation is B1 is equal to mu naught N1. So then, because N is equal to number of turns per unit length, so the equation will be like this. The magnetic flux linkage through the coil caused by the magnetic field of solenoid is flux is equal to B1A. Okay, again I repeat, the magnetic flux linkage through the coil caused by the magnetic field by solenoid is equal to flux 2 is equal to B1A. So equation tu akan jadi B1 kita tahu mu naught N1 I1 over L darab dengan A. So then kita tahu lagi the change of magnetic flux in coil 2 is due to the change of current in coil 1. MI1 is equal to N2 flux 2. So kita dah dapatkan M. N2 flux 2 is mu naught I1 I1A over I1L. Okay, so then equation kita akan jadi, kita cancel I dengan I, mu naught N1 N2 A over N. So this is our equation for the mutual inductance. So then, if no magnetic flux linkage, so we have flux 1 is equal to flux 2. And the equation will be like this, M equal to mu naught N1 N2 A over L. Pun sama juga, M1 pun boleh. Okay, where mu naught is permeability of free space, N1 is number of turns is solenoid 1, N2 number of turns going 2, L is the length of solenoid, A is the cross-sectional of solenoid. Okay, then bye. Okay, that's all for magnetic induction. Okay, again we have magnetic flux, induced Emf, which is divided into two, Faraday's law and Lenz law. And then we have Faraday summarized the ways it can be induced in a coil, in a moving conductor, variation angle and variation current. We also have to know this one. Okay. In calculation, all in calculation you learn in tutorial. Okay, you have this one is for the rotating coil, for the self-induction, mutual induction, and also the energy stored. You have to know all this. Okay. Di sini tak ada risau sebabnya nanti akan disediakan you all punya formula untuk PSPM. Okay, bye then. Good luck. Thanks. Bye.